30 performance testing, interview question and answers. High-load scenarios that actually win interviews.
Why this series exists?
Most performance testing interviews do not fail candidates because they lack tool knowledge. They fail because candidates cannot explain how systems behave under load. This series is designed to fix that. Each scenario represents a real interview challenge where the interviewer is testing your thinking, not your ability to run a load test.
How these 30 scenarios are organized.
To avoid overwhelming you, the scenarios are grouped by the type of performance thinking being tested. Each category focuses on a specific class of mistakes candidates make, and the mental models senior engineers use instead. You can treat each category as a mini reference guide.
The 6 categories that we are covering.
Following are the 6 categories into which that 30 scenarios are divided into and what we will cover on those categories. 1. User load and traffic modeling, 5 scenarios. Understanding how users actually generate load. 2. Bottleneck identification, 5 scenarios. Finding the real constraint, not the obvious one. 3. Latency, throughput, and SLAs, 5 scenarios. Separating meaningful metrics from misleading ones. 4. Scalability and elasticity, 5 scenarios, where cloud promises break down under pressure. 5. Failure and degradation, 5 scenarios, testing systems on their worst day, not their best. 6. Data and caching, 5 scenarios, how state and data size quietly dominate performance.
Category A, user load and traffic modeling.
This category focuses on the difference between scripting load and simulating reality. Interviewers use these questions to see whether you understand how real users behave, how traffic forms over time, and why naive load models produce useless results.
Scenarios covered in this category.
1. The 1 million user myth. 2. The flash sale spike. 3. The 9 a.m. login storm. 4. The reader-writer deadlock. 5. The zero think time error. Scenario 1. The 1 million user myth.
The interview challenge.
You're asked to performance test a system for 1 million users. The immediate reaction is to simulate 1 million threads or virtual users. The test fails, the load generator collapses, or the numbers make no sense. The interviewer watches closely. What you do next determines the outcome.
Where most candidates go wrong.
Most candidates assume that users equal concurrency. They try to brute force the number without questioning what those users are actually doing. This turns the test into a stress experiment on the load generator rather than a meaningful evaluation of the system.
How senior engineers think about this.
A senior engineer reframes the problem before touching any tool. 1 million users does not mean 1 million simultaneous requests. 2. Real users spend most of their time idle, not clicking continuously. 3. What matters is the resulting request rate and concurrency shaped by think time.
The interview-winning answer.
I would not simulate 1 million threads. Instead, I would estimate user behavior to derive a realistic request rate. If 1 million users perform 1 action per minute, that's roughly 16,000 requests per second. I would design a load test that generates that RPS with realistic pacing, and then validate latency, error rates, and saturation behavior at that level.
Why this matters in real systems.
Overestimating concurrency leads to misleading results, wasted capacity, and incorrect conclusions. Accurate performance testing models how users behave over time, not how many accounts exist in a database.
Follow-up 1. How do you estimate think time without production data?
Answer: you start with reasonable assumptions based on product type and human interaction speed, then validate them with stakeholders. Precision is less important than modeling realistic behavior.
Follow-up 2. What if the interviewer insists on 1 million concurrent users?
Answer: I would clarify whether they mean connections, sessions, or requests. If concurrency truly matters, I would design a targeted test focused on connection handling rather than throughput.
Follow-up 3. Curveball. When does 1 million concurrent users actually matter?
Answer: it matters for systems built around long-lived connections, such as chat platforms or WebSocket-based systems, where memory and file descriptor limits dominate. This scenario establishes a core principle. Performance testing is about translating vague scale requirements into concrete, testable models. Strong candidates always clarify before they simulate. Next, we move to a very different challenge. A flash sale where traffic explodes in seconds, and systems that handle steady load collapse instantly. Scenario 2, the flash sale spike.
The interview challenge.
A product team runs a flash sale. Traffic increases by 500 times within a few seconds. The load balancer stays healthy, servers are running, but users start seeing timeouts and failures almost immediately. The interviewer asks, why did a system that handles steady load perfectly fall apart so fast?
Where most candidates go wrong.
Most candidates answer by talking about overall capacity. They say the system needs more servers or bigger instances. This misses the point. The system did not fail because of total volume, but because of how fast the load arrived.
How senior engineers think about this.
A senior engineer immediately separates volume from arrival rate. 1. Steady-state capacity does not protect against sudden bursts. 2. Queues, thread pools, and connection limits absorb spikes first. 3. If arrival rate exceeds processing rate, latency explodes before errors appear.
The interview-winning answer.
I would explain that flash sales are burst problems, not capacity problems. Even if the system can handle the average traffic, a sudden spike overwhelms queues and thread pools. I would design tests that ramp traffic aggressively, observe queue depth and tail latency, and introduce rate limiting or load shedding to protect the system during spikes.
Why this matters in real systems.
Many outages happen in the first seconds of traffic spikes, not at peak averages. Systems that lack burst protection fail fast even when they appear well provisioned. Designing for arrival rate is often more important than designing for total volume.
Follow-up 1. How would you test burst traffic differently from steady load?
Answer: I would use rapid ramp-up or step load tests instead of gradual increases. The goal is to exceed arrival rate limits quickly and observe queue growth, latency spikes, and rejection behavior.
Follow-up 2. Why don't average metrics reveal this problem?
Answer: averages smooth out short-lived spikes. By the time averages change, users have already experienced timeouts. Tail latency and queue depth reveal burst failures much earlier.
Follow-up 3. Curveball. Why not just auto-scale faster?
Answer: auto-scaling reacts after the spike is detected, and instances take time to become ready. Burst failures occur faster than scaling can respond, so protection must exist before scaling helps. This scenario teaches that handling bursts is about controlling arrival rate, not just adding capacity. Strong candidates distinguish between volume and speed. In the next scenario, we will look at a system that fails at the same time every morning, even though traffic volume appears normal. Scenario 3, the 9 a.m. login storm.
The interview challenge.
A system runs smoothly all day, but every Monday at exactly 9:00 a.m., users start complaining about slow logins and intermittent failures. There is no deploy, no spike in total daily traffic, and nothing unusual in the dashboards at first glance. The interviewer asks why the system keeps failing at the same time.
Where most candidates go wrong.
Most candidates focus on average traffic volume and conclude that capacity is sufficient. They look for recent code changes or infrastructure issues, assuming something must be broken rather than recognizing a predictable traffic pattern.
How senior engineers think about this.
A senior engineer immediately thinks in terms of synchronized behavior. 1. Login traffic is highly bursty and synchronized by human schedules. 2. Many users authenticate at the same moment, not evenly over time. 3. Authentication paths often hit shared resources like databases, caches, or identity providers.
The interview-winning answer.
I would explain that this is a classic login storm caused by synchronized user behavior. Even if total traffic is moderate, thousands of users logging in simultaneously overload authentication components. I would design tests that simulate synchronized login bursts, measure queue depth and tail latency, and introduce controls such as request smoothing, caching of auth data, or rate limiting to protect the login path.
Why this matters in real systems.
Many production incidents are caused by predictable human behavior rather than random spikes. Systems fail not because of scale, but because everyone does the same thing at the same time. Recognizing synchronization is key to realistic performance testing.
Follow-up 1. How would you simulate a login storm in a test?
Answer: I would trigger a large number of login requests within a very short time window, minimizing think time. to reproduce synchronized behavior rather than spreading requests evenly.
Follow-up 2. Why does this usually affect authentication more than other APIs?
Answer: authentication often involves shared state, cryptographic operations, and external identity systems. These components are more sensitive to bursts than stateless read endpoints.
Follow-up 3. Curveball. Why doesn't auto-scaling fix login storms?
Answer: because the storm arrives faster than scaling can react, and new instances still contend for the same backend resources. Without smoothing or protection, scaling alone is ineffective. This scenario highlights that time-based patterns matter as much as volume. Strong candidates recognize synchronized user behavior as a first-class performance risk. Next, we'll examine a system that performs perfectly for reads, but collapses as soon as users start writing data. Scenario 4. The reader-writer deadlock.
The interview challenge.
A system performs extremely well when users are only reading data. Pages load fast, APIs are responsive, and dashboards look healthy. The moment users start writing data, posting comments, placing orders, updating profiles, performance collapses. The interviewer asks why read-heavy systems often fail the instant writes appear.
Where most candidates go wrong.
Most candidates assume the database is simply underpowered. They suggest adding replicas, increasing instance size, or scaling horizontally. This ignores the fact that the system was already fast for reads, and that writes introduce a fundamentally different kind of contention.
How senior engineers think about this.
A senior engineer immediately thinks about coordination, not capacity one. Reads are often concurrent and cheap, while writes require coordination and locking. 2. Write operations can block readers through locks, indexes, or transactional guarantees. 3. A small number of writes can serialize large portions of the system. SQL example. Write locks blocking concurrent readers during updates. Disclaimer: always test code in a non-production environment. This code shows a write operation that acquires locks on the affected rows or indexes. While the transaction is open, other queries may block, including reads, depending on the isolation level. Under load, even short write transactions can stall large numbers of readers.
The interview-winning answer.
I would explain that the system is optimized for concurrent reads, but not for coordinated writes. Writes introduce locks and serialization that block readers and increase queuing. I would test mixed read-write workloads, measure lock wait time, and redesign critical paths by shortening transactions, batching writes, or separating read and write workloads.
Why this matters in real systems.
Many real-world outages happen when systems transition from read-only to interactive. The cost of coordination dominates performance long before CPU or memory limits are reached. Performance testing must include realistic write behavior to expose this risk.
Follow-up 1. How would you detect this problem during testing?
Answer: I would look at lock wait time, transaction duration, and queue depth rather than CPU usage. Rising wait times with low resource utilization strongly indicate coordination bottlenecks.
Follow-up 2. Why do read replicas not fully solve this?
Answer: because writes still need to coordinate on the primary system. Replicas help scale reads, but write paths often remain serialized and become the limiting factor.
Follow-up 3. Curveball. When can reads continue during writes?
Answer: with snapshot isolation or MVCC, reads can proceed without blocking, but this shifts cost to storage and cleanup. Understanding the database's isolation model is critical. This scenario shows why read-heavy benchmarks can be dangerously misleading. Systems often fail not when load increases, but when coordination begins. Next, we'll look at a subtle testing mistake where eliminating human pause time makes systems appear far more capable than they really are. Scenario 5. The zero think time error.
The interview challenge.
Your load test reports that the system can handle 5,000 requests per second with acceptable latency. Confident in the result, the team ships. In production, users immediately complain that the system feels slow and unresponsive. The interviewer asks, why did a test that looked excellent produce such poor real-world experience?
Where most candidates go wrong.
Most candidates trust the reported throughput and assume the production issue must be unrelated. They overlook a subtle but critical mistake. The load test removed all human pause time, creating an artificial traffic pattern no real user ever generates.
How senior engineers think about this.
A senior engineer immediately questions how the load was generated. 1. Real users pause between actions to read, think, and react. 2. Zero think time turns a user simulation into a tight loop generator. 3. Artificially synchronized requests distort queuing, latency, and contention behavior.
The interview-winning answer.
I would explain that the test measured how fast the system can respond to non-stop requests, not how it behaves with real users. By removing think time, the test inflated concurrency and hid user-perceived latency. I would redesign the test to include realistic pauses between actions, and then reevaluate P95 and P99 latency under that model.
Why this matters in real systems.
Zero think time tests often make systems look faster than they feel. They optimize for throughput at the cost of responsiveness. Production users experience delay during pauses, page transitions, and retries, none of which exist in artificial loops.
Follow-up 1. How do you choose realistic think time values?
Answer: I base them on the type of action being performed. Simple clicks may pause for seconds, while form submissions or checkouts involve longer pauses. Estimates can be refined later with real user data.
Follow-up 2. Why does removing think time often increase reported throughput?
Answer: because the load generator continuously issues requests without waiting, maximizing concurrency. This measures the system's raw processing speed rather than its ability to serve users comfortably.
Follow-up 3. Curveball. When is zero think time testing still useful?
Answer: it can be useful for identifying absolute capacity limits or stress testing specific components. However, it should never be confused with a realistic user performance test. This scenario reinforces a core principle. Performance tests must model human behavior, not just machine capability. Removing pauses turns insight into illusion. This concludes Category A. Next, we move into bottleneck detection, where systems fail even though nothing appears overloaded.
Category B. Bottleneck identification, the detective work.
This category focuses on one of the hardest interview skills to fake, identifying the real bottleneck when everything looks wrong or nothing looks wrong. These scenarios test whether you chase symptoms or reason about constraints. Interviewers use them to see if you can isolate contention, waiting, and saturation without guessing.
Scenarios in this category.
1. The CPU lie. 2. The I or O choke. 3. The silent lock. 4. The connection pool drought. 5. The blame game app versus dependency.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer. Scenario-based questions and answers. System design questions and answers where almost 90% of the people are failing to answer. With detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Scenario 6. The CPU lie.
The interview challenge.
Your monitoring shows the service running at nearly 100% CPU. Latency is climbing, and requests are timing out. The obvious conclusion is that the service needs more CPU. The interviewer asks why adding more cores sometimes makes performance worse instead of better.
Where most candidates go wrong.
Most candidates treat CPU utilization as a direct measure of useful work. They immediately propose vertical scaling, assuming that more cores always mean more throughput. This ignores how operating systems schedule work under contention.
How senior engineers think about this.
A senior engineer looks beyond the headline CPU number 1. High CPU can mean useful computation or excessive context switching. 2. When threads outnumber cores, the OS spends time switching rather than executing. 3. More cores can increase coordination overhead instead of reducing latency.
The interview-winning answer.
I would not assume CPU saturation means we need more cores. I would check user time versus system time and look for excessive context switching. If the CPU is busy managing threads rather than executing application logic, I would reduce concurrency or tune thread pools before scaling the instance.
Why this matters in real systems.
In production systems like web servers and databases, uncontrolled concurrency often reduces throughput. Pinning workloads, limiting threads, or lowering parallelism frequently improves performance more than adding hardware.
Follow-up 1. How do you tell if CPU time is being wasted on context switching?
Answer: I would look at system CPU time and context switch metrics. High system time combined with rising latency indicates the CPU is managing contention rather than doing useful work.
Follow-up 2. Why doesn't auto-scaling always help here?
Answer: because auto-scaling adds more threads and processes competing for shared resources. If contention is the issue, scaling amplifies coordination costs instead of relieving pressure.
Follow-up 3. Curveball. When does adding CPU actually help?
Answer: when the workload is CPU bound with low contention and threads scale efficiently. In those cases, user time dominates system time and throughput increases predictably with cores. This scenario teaches that CPU is a misleading signal unless you understand how it is being consumed. Bottleneck identification starts with distinguishing work from waiting. Next, we will examine a system that looks idle on CPU and memory, yet becomes completely unresponsive due to I or O waiting. Scenario 7. The I or O choke.
The interview challenge.
Latency is climbing and requests are timing out. CPU usage is low, memory is stable, nothing looks overloaded. The service is technically up but feels frozen. The interviewer asks, how can a system be slow when it is barely using CPU?
Where most candidates go wrong.
Most candidates fixate on CPU and memory. When both look healthy, they conclude the problem must be in the application code or network. They overlook the fact that a system can be blocked waiting for I or O while appearing idle.
How senior engineers think about this.
A senior engineer immediately considers waiting states 1. Low CPU does not mean work is progressing. It may mean threads are blocked. 2. Disk and network I or O introduce wait time that is invisible in CPU metrics. 3. When I or O queues fill, latency increases even though utilization looks low.
The interview-winning answer.
I would explain that this is an I or O wait problem, not a CPU problem. I would look at disk I or O wait time, queue depth, and request latency at the storage layer. If threads are blocked waiting on disk or network I or O, adding CPU won't help. The fix is to reduce I or O per request, improve caching, or move to faster storage.
Why this matters in real systems.
Many production systems fail due to slow disks, overloaded network storage, or synchronous I or O in hot paths. These failures are often misdiagnosed because traditional dashboards emphasize CPU and memory over waiting.
Follow-up 1. Which metric would you check first to confirm I or O wait?
Answer: I would check I or O wait time and disk queue depth. High wait with low CPU indicates threads are stalled waiting for storage operations to complete.
Follow-up 2. Why does this often show up only under load?
Answer: because I or O contention increases non-linearly. A small increase in concurrent requests can overwhelm disks or network storage, causing queues to form suddenly.
Follow-up 3 Curveball. Why does caching sometimes make this worse?
Answer: if caching is poorly designed, cache misses can synchronize requests and amplify I or O bursts. This creates sudden spikes in disk access rather than smoothing load. This scenario reinforces a key diagnostic skill. Low CPU does not imply health. Performance bottlenecks often hide in waiting, not work. Next, we'll look at a failure mode where requests block each other silently due to locking, even though the database appears idle. Scenario 8, the silent lock.
The interview challenge.
Requests are timing out across the system. Latency keeps increasing. CPU usage is low. Database metrics look normal. There are no obvious errors. The interviewer asks, how can a system grind to a halt when nothing appears busy?
Where most candidates go wrong.
Most candidates assume that if the database CPU is low, the database cannot be the bottleneck. They move on to networking or application code, missing the fact that work can be blocked without consuming CPU.
How senior engineers think about this.
A senior engineer immediately suspects invisible contention. 1. Locks block progress without increasing CPU usage. 2. Waiting transactions consume time, not resources. 3. A single long-running transaction can stall many fast ones. SQL code. Long-running transactions silently blocking concurrent requests. Disclaimer: always test code in a non-production environment. This code acquires a write lock on the affected row. While the transaction stays open, other reads or writes that need this row will block. Under load, many requests queue behind this lock, causing timeouts without increasing CPU usage.
The interview-winning answer.
I would explain that this is a lock contention problem. A long-running transaction is holding locks and forcing other requests to wait. I would inspect lock wait times, transaction duration, and blocked queries, then reduce transaction scope, shorten lock duration, or redesign the workflow to avoid shared mutable state.
Why this matters in real systems.
Many severe outages are caused by locking, not load. Locks create serialized access paths that collapse concurrency long before CPU or memory limits are reached.
Follow-up 1. How do you detect lock contention during a test?
Answer: I would monitor lock wait time, blocked queries, and transaction duration. Rising wait times with stable CPU strongly indicate locking issues.
Follow-up 2. Why is this often missed in dashboards?
Answer: because locks represent waiting, not work. Standard dashboards focus on utilization metrics, which stay low while requests block.
Follow-up 3 Curveball. Why do small datasets make this worse?
Answer: because more requests target the same rows or indexes. Hot spots increase contention, making locks far more likely even under moderate load. This scenario shows that the most dangerous bottlenecks are often invisible. When systems stall quietly, locking is one of the first suspects. Next, we'll examine a system where application servers sit idle, waiting endlessly for a resource they can't obtain. Scenario 9. The connection pool drought.
The interview challenge.
Application servers are running, CPU is low, memory is stable, and request volume has not changed. Yet latency keeps increasing and requests start timing out. Thread dumps show many threads waiting. The interviewer asks, how can an application be idle and stuck at the same time?
Where most candidates go wrong.
Most candidates assume the database is slow or unavailable. They focus on query optimization or scaling the database, missing the fact that the application may not even be reaching the database due to resource exhaustion upstream.
How senior engineers think about this.
A senior engineer immediately considers shared finite resources. 1. Database connections are a limited pool, not an infinite resource. 2. Threads block while waiting for a free connection. 3. Blocked threads inflate latency without consuming CPU. Java code. Small database connection pool causing request blocking under load. Disclaimer: always test code in a non-production environment. This code limits the application to 10 concurrent database connections. When more than 10 requests need the database at the same time, additional threads block while waiting for a connection. Under load, this waiting dominates latency even though CPU remains low.
The interview-winning answer.
I would explain that this is a connection pool exhaustion issue. Threads are blocked waiting for database connections, not executing queries. I would inspect pool utilization, wait time, and request concurrency, then right-size the pool or reduce concurrent database access through batching, caching, or asynchronous workflows.
Why this matters in real systems.
Connection pools protect databases, but misconfigured pools quietly throttle applications. Many performance incidents are caused by threads waiting, not slow queries.
Follow-up 1. Why not just increase the pool size aggressively?
Answer: because the database also has limits. Increasing the pool can shift the bottleneck downstream and cause database overload or instability.
Follow-up 2. How do you confirm pool exhaustion quickly?
Answer: I would check connection pool metrics such as active connections, wait time, and queue length. High wait time with low CPU strongly indicates pool contention.
Follow-up 3. Curveball. Can this happen even with fast queries?
Answer: yes. Even very fast queries consume a connection while executing. High concurrency alone can exhaust the pool, independent of query speed. This scenario teaches that finite shared resources often become bottlenecks before any system looks busy. Waiting hides inside pools. Next, we'll look at a diagnostic challenge, where teams argue about whether the application or a dependency is truly at fault. Scenario 10, the blame game, app versus dependency.
The interview challenge.
An API is slow and users are complaining. Application metrics show increased latency. Developers blame the database. The database team says everything is healthy. The network team suspects connectivity issues. The interviewer asks, how do you determine where the bottleneck actually is without guessing?
Where most candidates go wrong.
Most candidates pick a side based on intuition or team boundaries. They argue from assumptions instead of evidence, jumping between components without isolating the problem. This turns diagnosis into opinion rather than engineering.
How senior engineers think about this.
A senior engineer treats the system as a set of measurable boundaries. 1. Latency must be decomposed across components, not discussed globally. 2. Each dependency call has an entry and exit point that can be measured. 3. Isolation, not blame, is the fastest path to truth.
The interview-winning answer.
I would break end-to-end latency into segments and measure each boundary explicitly. Using tracing or targeted timing, I would show where time is spent, inside the application, waiting on the database, or blocked on the network. This removes opinion from the discussion and allows the slow component to be identified objectively.
Why this matters in real systems.
Many outages last longer than necessary because teams argue instead of isolating. Engineers who can turn ambiguity into evidence resolve incidents faster and build trust across teams.
Follow-up 1. What if distributed tracing is not available?
Answer: I would add temporary timing logs at request boundaries or use synthetic probes to measure latency between components. Even coarse measurements can reveal where time is being spent.
Follow-up 2. Why not rely on averages from dashboards?
Answer: averages hide tail behavior and short-lived stalls. Isolating components requires looking at individual request paths or high percentile latency.
Follow-up 3. Curveball. What if every component looks slow?
Answer: that often indicates a shared dependency or contention point. I would look for common resources like networks, disks, or coordination services that affect all components simultaneously. This scenario closes the bottleneck identification category. Strong candidates replace blame with measurement and turn complex systems into debuggable ones. Next, we move into latency, throughput, and SLA trade-offs, where systems technically succeed while users still suffer.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing, job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer. Scenario-based questions and answers, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Category C, latency, throughput, and SLAs.
This category focuses on metrics that look impressive on dashboards but quietly destroy user experience. Interviewers use these scenarios to test whether you understand the trade-offs between speed, volume, and guarantees. The theme here is simple. Numbers can lie if you don't know what they represent.
Scenarios in this category.
1. The throughput trap. 2. The average fallacy. 3. The microservices murder tail latency. 4. The SLA breach optimize or scale. 5. The retry storm. Scenario 11. The throughput trap.
The interview challenge.
Your load test shows the system successfully handling 10,000 requests per second. The team celebrates the result. However, users complain that pages take several seconds to load. The interviewer asks, how can a system meet its throughput target and still deliver a terrible user experience?
Where most candidates go wrong.
Most candidates equate higher throughput with better performance. They assume that if requests per second are high, the system must be healthy. This ignores how long individual users are actually waiting for responses.
How senior engineers think about this.
A senior engineer separates volume from experience. 1. Throughput measures how much work is done, not how fast users are served. 2. Systems can increase throughput by queuing requests, increasing wait time. 3. Latency, especially at high percentiles, defines user satisfaction.
The interview-winning answer.
I would explain that throughput and latency are trade-offs, not interchangeable goals. The system is maximizing throughput by allowing requests to queue, which inflates user wait time. I would focus the evaluation on P95 and P99 latency, and redesign the test to enforce latency budgets rather than celebrating raw request volume.
Why this matters in real systems.
Many real systems technically succeed by processing requests eventually, while users abandon them due to delay. Optimizing for throughput alone often converts fast failure into slow frustration.
Follow-up 1. Why does throughput often increase as latency worsens?
Answer: because queuing allows the system to accept more requests even when it cannot serve them promptly. Work piles up, increasing total completed requests while users wait longer.
Follow-up 2. How would you redesign a test to avoid this trap?
Answer: I would enforce latency thresholds and fail the test when high percentile latency exceeds acceptable limits, even if throughput targets are met.
Follow-up 3. Curveball. Is high throughput ever the right primary goal?
Answer: yes, for batch or offline systems where completion time matters more than individual request latency. For user-facing systems, latency must dominate. This scenario establishes a critical mental shift. Success metrics must reflect user experience, not just system output. Next, we'll examine why average response time is one of the most misleading numbers in performance testing. Scenario 12, the average fallacy.
The interview challenge.
Your dashboard shows an average response time of 200 milliseconds. On paper, this looks excellent. Yet a noticeable percentage of users are abandoning sessions and reporting slowness. The interviewer asks if the average is good. Why are users unhappy?
Where most candidates go wrong.
Most candidates trust the average and dismiss user complaints as edge cases. They assume outliers are irrelevant and focus optimization efforts elsewhere, believing the system is already performing well.
How senior engineers think about this.
A senior engineer treats averages as a warning sign, not a conclusion one. Averages hide distribution and mask extreme experiences. 2. A small percentage of very slow requests can dominate user perception. 3. Tail latency, not the mean, defines perceived performance.
The interview-winning answer.
I would explain that average latency is not representative of user experience. I would analyze latency percentiles, especially P95 and P99, to understand how the slowest users are affected. If those tails are high, the system is failing users even if the average looks good.
Why this matters in real systems.
In production systems, a small fraction of slow requests can drive churn, retries, and support tickets. Optimizing the average often leaves the worst experiences untouched.
Follow-up 1. Why do averages remain stable while P99 explodes?
Answer: because most requests are still fast. As long as the majority complete quickly, the mean stays low even when a minority experiences severe delays.
Follow-up 2. Which percentile should you care about?
Answer: it depends on the product, but P95 or P99 usually aligns with user pain. The key is choosing a percentile that reflects unacceptable experience, not statistical convenience.
Follow-up 3. Curveball. Can optimizing for P99 hurt the system?
Answer: yes. Over-optimizing the tail can reduce throughput or increase cost. The goal is to balance tail latency against capacity and budget, not eliminate it entirely. This scenario teaches that averages are comfort metrics. Senior engineers diagnose performance using distributions, not single numbers. Next, we'll see how combining multiple fast services can mysteriously create slow end-to-end behavior. Scenario 13. The microservices murder tail latency.
The interview challenge.
Each individual microservice responds quickly when tested in isolation. Service A is fast. Service B is fast. Service C is fast. Yet the end-to-end user request that calls all of them is painfully slow. The interviewer asks, how can multiple fast services produce a slow system?
Where most candidates go wrong.
Most candidates assume one service must be lying about its performance. They start hunting for a single slow dependency, expecting to find one obvious culprit. This misses the systemic nature of tail latency.
How senior engineers think about this.
A senior engineer thinks in terms of probability and aggregation. 1. Each service has its own latency distribution, not a fixed response time. 2. Tail latency compounds when services are called sequentially or in parallel. 3. Even small P99 delays multiply across fan-out architectures.
The interview-winning answer.
I would explain that this is a tail latency amplification problem. Even if each service is fast most of the time, their worst-case latencies accumulate across calls. I would analyze end-to-end P99 latency, reduce fan-out where possible, introduce parallelism carefully, and apply timeouts or hedging to control tail behavior.
Why this matters in real systems.
Many microservice architectures fail not because services are slow, but because their tails align. As systems grow, tail latency becomes the dominant driver of user experience.
Follow-up 1. Why don't service-level SLAs prevent this?
Answer: because SLAs are usually defined per service, not end-to-end. A system can meet every individual SLA and still violate the user-facing SLA.
Follow-up 2. How does parallel fan-out make this worse?
Answer: in parallel calls, the slowest response determines completion. As the number of parallel calls increases, the probability of hitting a slow tail increases dramatically.
Follow-up 3. Curveball. What's one practical mitigation?
Answer: setting aggressive timeouts and returning partial results when possible limits tail amplification. Designing APIs to tolerate missing data often improves perceived performance. This scenario explains why microservices demand different performance thinking than monoliths. As systems fan out, tails dominate. Next, we'll face a decision interviewers love. When an SLA is breached, do you optimize the code or scale the infrastructure? Scenario 14. The SLA breach: optimize or scale.
The interview challenge.
Your system has a strict SLA of 500 milliseconds. Under peak load, P95 latency rises to 600 milliseconds. Error rates are low, throughput is stable, and nothing is technically broken. The interviewer asks, do you optimize the code or add more capacity?
Where most candidates go wrong.
Most candidates answer immediately with their personal bias. Some default to scaling because it is fast. Others insist on code optimization because it feels principled. Both miss the fact that this is a decision problem, not a reflex.
How senior engineers think about this.
A senior engineer evaluates cost, risk, and evidence before acting one. Is the latency increase linear with load or sharply nonlinear? 2. Does the system show signs of saturation or contention? 3. What is the cost and risk of scaling versus changing code?
The interview-winning answer.
I would explain that the decision depends on where the latency comes from. If the system is saturating cleanly, scaling may restore the SLA quickly. If latency grows nonlinearly due to contention or queuing, scaling may make it worse. I would gather evidence first, then choose the lowest risk action that restores the SLA.
Why this matters in real systems.
Blind optimization or blind scaling both waste time and money. Strong engineers treat SLA breaches as decision problems grounded in system behavior, not ideology.
Follow-up 1. What's the fastest safe way to restore an SLA?
Answer: the fastest safe action is the one that reduces user impact without introducing new risk. Often that means temporary scaling combined with investigation.
Follow-up 2. How do you tell if scaling will help?
Answer: I look for linear scaling behavior and low contention. If adding capacity reduces latency proportionally in tests, scaling is likely effective.
Follow-up 3. Curveball. When is doing nothing the right choice?
Answer: if the SLA breach is transient and with an error budget, immediate action may cause more harm than waiting. Not every breach requires intervention. This scenario teaches that performance decisions are trade-offs, not absolutes. Senior engineers justify actions with evidence. Next, we'll look at a failure mode, where a small retry configuration change silently doubles the load and brings systems down. Scenario 15, the retry storm.
The interview challenge.
A minor dependency glitch occurs. Error rates rise slightly. Minutes later, traffic doubles, latency explodes, and the entire system collapses. The interviewer asks, how did a small failure turn into a full outage?
Where most candidates go wrong.
Most candidates treat retries as a safety mechanism. They assume retries always improve reliability and focus on increasing retry counts or timeouts, not realizing that retries multiply load during partial failure.
How senior engineers think about this.
A senior engineer treats retries as controlled explosives. 1. Retries increase request volume during failure, not during success. 2. Partial failures are the most dangerous case for retries. 3. Unbounded or poorly tuned retries amplify load and queuing. YAML config, retry policy that amplifies load during partial failure. Disclaimer: always test code in a non-production environment. This code shows a retry configuration that allows each failed request to be retried up to 5 times. During partial failures, these retries multiply incoming traffic, increasing pressure on already degraded dependencies.
The interview-winning answer.
I would explain that retries amplify load during partial failures and can quickly overwhelm the system. I would limit retries, add exponential backoff, and disable retries entirely when error budgets are burning. The goal is to fail fast and protect the system, not chase success at all costs.
Why this matters in real systems.
Retry storms are one of the most common causes of cascading failures in distributed systems. Systems often die not from the original fault, but from the traffic created by retries.
Follow-up 1. Why are retries most dangerous during partial failures?
Answer: because some requests succeed and some fail, triggering retries while the system is already under stress. This creates unpredictable load spikes that exceed capacity.
Follow-up 2. How do you make retries safer?
Answer: by adding exponential backoff, jitter, strict retry limits, and circuit breakers. Retries must slow down under failure, not speed up.
Follow-up 3. Curveball. When should retries be disabled completely?
Answer: when latency SLOs are burning or downstream systems are saturated. In those cases, Fast failure preserves overall system health better than delayed success. This scenario concludes Category C. It reinforces a core truth. Reliability mechanisms can become failure mechanisms when misused. Next, we move into scalability and elasticity, where cloud systems behave very differently from expectations under real load.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing, job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer. Scenario-based questions and answers. System design questions and answers where almost 90% of the people are failing to answer. With detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Category D, Scalability and Elasticity.
This category examines the gap between how cloud scalability is marketed and how it actually behaves under pressure. Interviewers use these scenarios to see whether you understand control loops, shared bottlenecks, and lifecycle delays, not just how to turn on auto-scaling.
Scenarios in this category.
1. The horizontal plateau. 2. The auto-scaling lag. 3. The serverless cold start. 4. The scale-down crash. 5. The wall max capacity test. Scenario 16. The horizontal plateau.
The interview challenge.
You double the number of application instances. Performance should improve. Instead, throughput barely changes and latency remains high. The interviewer asks, why didn't horizontal scaling deliver linear improvement?
Where most candidates go wrong.
Most candidates assume horizontal scaling always works if enough instances are added. They focus on instance count and ignore the possibility that something else in the system cannot scale the same way.
How senior engineers think about this.
A senior engineer looks for shared constraints. 1. Not all components scale horizontally at the same rate. 2. Databases, caches, and networks often become shared bottlenecks. 3. Adding instances can increase contention on downstream resources.
The interview-winning answer.
I would explain that horizontal scaling hit a shared bottleneck. While application instances scaled, a downstream dependency did not. I would identify the limiting component, measure its saturation point, and either scale it separately or reduce pressure through caching, batching, or architectural changes.
Why this matters in real systems.
Many cloud systems plateau because only part of the architecture scales. Horizontal scaling without bottleneck analysis leads to wasted cost and no performance gain.
Follow-up 1. How do you identify the shared bottleneck quickly?
Answer: I would correlate latency increases with saturation metrics across dependencies. The component whose latency, or queue depth, rises first is usually the bottleneck.
Follow-up 2. Why does scaling sometimes make latency worse?
Answer: because additional instances increase concurrent requests to the bottleneck, amplifying contention and queuing downstream.
Follow-up 3. Curveball. When does horizontal scaling actually work well?
Answer: when workloads are stateless and dependencies scale proportionally. In those cases, throughput increases linearly until a new bottleneck appears. This scenario establishes a core scalability lesson. Scaling the wrong layer changes nothing. Next, we'll examine why auto-scaling often reacts too late to save user experience. Scenario 17. The auto-scaling lag.
The interview challenge.
Traffic spikes sharply. The auto-scaler triggers exactly as designed. New instances eventually come online. Despite this, users experience errors and severe latency for several minutes. The interviewer asks, if auto-scaling worked correctly, why did users still suffer?
Where most candidates go wrong.
Most candidates assume auto-scaling is an instant fix. They believe that once scaling triggers, capacity problems are solved. This ignores the time it takes to detect load, provision resources, and make instances ready to serve traffic.
How senior engineers think about this.
A senior engineer reasons in terms of control loops and delays. 1. Auto-scaling reacts after metrics cross thresholds, not before. 2. Provisioning, boot, and warm-up introduce unavoidable delays. 3. User impact occurs during the gap between demand and readiness.
The interview-winning answer.
I would explain that auto-scaling is reactive by design. The lag between detecting load and serving traffic creates a window where users are impacted. To address this, I would use predictive scaling, pre-warming capacity, aggressive rate limiting during spikes, or faster readiness paths so the system can absorb traffic before scaling completes.
Why this matters in real systems.
Many cloud outages happen during scale-up, not at steady state. Systems fail in the gap between intention and execution, where demand arrives faster than capacity.
Follow-up 1. Why can't auto-scaling simply react faster?
Answer: because metrics need time to accumulate, decisions need time to be evaluated, and infrastructure needs time to provision. These delays are inherent to distributed systems.
Follow-up 2. What's the safest way to protect users during scale-up?
Answer: rate limiting and load shedding protect existing capacity while new instances come online. This trades partial rejection for overall stability.
Follow-up 3. Curveball. When does auto-scaling work best?
Answer: when load changes gradually and instances become ready quickly. Auto-scaling excels at slow growth, not sudden spikes. This scenario teaches that elasticity has a speed limit. Designing for spikes requires protection before scaling helps. Next, we'll explore a cloud-native surprise, where serverless platforms trade cost savings for cold start latency. Scenario 18. The serverless cold start.
The interview challenge.
A serverless function performs well once traffic is flowing, but the first user after inactivity waits several seconds for a response. During spikes, many users hit this delay simultaneously. The interviewer asks, why does a platform designed for instant scale introduce noticeable latency?
Where most candidates go wrong.
Most candidates treat cold starts as a minor nuisance or assume they are purely a platform problem. They dismiss the impact or believe there is nothing they can do to mitigate it.
How senior engineers think about this.
A senior engineer reasons about life cycle and initialization cost. 1. Serverless platforms create execution environments on demand. 2. Cold starts include container startup, runtime initialization, and dependency loading. 3. Burst traffic can trigger many cold starts at once, compounding latency.
The interview-winning answer.
I would explain that cold starts are a trade-off of serverless elasticity. The platform optimizes for cost by not keeping instances warm. To reduce impact, I would minimize initialization work, reduce dependency size, use provision concurrency where available, or route latency-sensitive traffic to warm paths.
Why this matters in real systems.
Cold starts can dominate tail latency and directly affect user trust. In user-facing systems, a few seconds of delay is often more damaging than occasional errors.
Follow-up 1. Why do cold starts show up mostly in P99 latency?
Answer: because only the first requests hit cold environments. Most requests are served by warm instances, keeping averages low while the tail suffers.
Follow-up 2. Why doesn't auto-scaling eliminate cold starts?
Answer: auto-scaling still requires creating new execution environments. Scaling decisions do not remove initialization cost, they only trigger it.
Follow-up 3. Curveball. When are cold starts acceptable?
Answer: for background jobs, asynchronous workflows, or infrequent admin tasks where latency is not user visible. For interactive paths, they must be mitigated. This scenario highlights the hidden cost of convenience. Serverless systems trade idle capacity for startup latency. Next, we'll examine what happens when systems scale down and accidentally terminate users mid-request. Scenario 19, the scale-down crash.
The interview challenge.
Traffic drops after a peak period. Auto-scaling scales the service down to save cost. Minutes later, users report broken sessions, failed uploads, and interrupted requests. The interviewer asks, why did scaling down cause a user-facing incident?
Where most candidates go wrong.
Most candidates assume scale down is harmless because traffic is lower. They believe terminating instances simply removes unused capacity, overlooking the fact that those instances may still be handling active requests or state.
How senior engineers think about this.
A senior engineer reasons about lifecycle and termination semantics. 1. Instances can be terminated while still serving in-flight requests. 2. Session state or long-running operations may be tied to specific instances. 3. Graceful shutdown requires coordination, not just scaling decisions.
The interview-winning answer.
I would explain that scale down caused active instances to terminate before completing their work. To fix this, I would implement graceful termination, stop sending new traffic, allow in-flight requests to complete, drain connections, and only then shut down instances.
Why this matters in real systems.
Scale-down incidents are common in cloud environments because cost optimization is automated. Without graceful shutdown, systems trade cost savings for broken user experience.
Follow-up 1. How do you ensure in-flight requests complete?
Answer, I would use connection draining, termination grace periods, and readiness checks to stop new traffic while allowing existing requests to finish.
Follow-up 2. Why is this worse for stateful workloads?
Answer, because state tied to a specific instance is lost on termination. Without externalized state, users experience session loss or corrupted workflows.
Follow-up 3. Curveball. When is aggressive scale-down acceptable?
Answer, for stateless, idempotent, short-lived workloads where retries are cheap and user impact is minimal. This scenario teaches that elasticity cuts both ways. Scaling down safely is just as important as scaling up. Next, we'll determine how to find the absolute breaking point of a system without crashing production. Scenario 20. The wall max capacity test.
The interview challenge.
You are asked to determine the maximum capacity of a system before it fails, not degrades but truly breaks. The interviewer asks, how do you find this limit safely, and what does crossing it actually teach you?
Where most candidates go wrong.
Most candidates treat capacity testing as reckless stress testing. They either push traffic until everything crashes or avoid the question entirely, fearing production impact. Both approaches miss the purpose of the exercise.
How senior engineers think about this.
A senior engineer treats capacity as a measurable boundary. 1. Every system has a breakpoint where behavior changes abruptly. 2. Degradation patterns matter more than the exact failure point. 3. Capacity testing should be controlled, repeatable, and isolated.
The interview-winning answer.
I would explain that the goal is to find the system's breakpoint without causing harm. I would run controlled load increases in a staging or isolated environment, watch for nonlinear latency growth, queue buildup, or error spikes, and stop once the system shows instability. That breakpoint defines safe operating limits and informs scaling and protection strategies.
Why this matters in real systems.
Systems rarely fail gracefully beyond their limits. Knowing where the wall is allows teams to design alerts, rate limits, and safeguards before users ever experience catastrophic failure.
Follow-up 1. Why is finding the wall better than guessing capacity?
Answer, because real systems fail non-linearly. Empirical testing reveals behaviors that models and assumptions miss.
Follow-up 2. What signals tell you to stop the test?
Answer, rapidly rising tail latency, queue growth, error spikes, or recovery instability indicate the system is approaching unsafe territory.
Follow-up 3. Curveball. Should you ever test this in production?
Answer, only with strict safeguards such as traffic shaping, canaries, and instant rollback. Production tests must prioritize user safety over precision. This scenario completes Category D. It reinforces that scalability is not infinite and must be understood empirically. Next, we move into failure and degradation scenarios, where systems are tested on their worst day rather than their best.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, scenario-based questions and answers, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Category E, Failure and Degradation.
This category focuses on how systems behave on their worst day, not their best. Interviewers use these scenarios to test whether you understand graceful degradation, isolation, and recovery under pressure. These are not about preventing failure entirely, but about controlling blast radius when failure is inevitable.
Scenarios in this category:
1. The partial failure. 2. The feature flag save. 3. The infinite queue. 4. The fail fast test. 5. The recovery limbo. Scenario 21. The partial failure.
the interview challenge.
A critical dependency, such as a payment gateway or recommendation service, starts failing. Other parts of the system are still healthy. Instead of degrading gracefully, the entire application becomes slow or unusable. The interviewer asks, why did a partial failure take down the whole system?
Where most candidates go wrong.
Most candidates assume dependencies either work or fail completely. They design systems as if partial failure is rare, and during incidents, they focus on restoring the dependency instead of isolating its impact.
How senior engineers think about this.
A senior engineer expects partial failure as the default state. 1. Dependencies often fail slowly or intermittently, not all at once. 2. Blocking calls to unhealthy dependencies consume threads and queues. 3. Without isolation, failure propagates upstream rapidly.
The interview-winning answer.
I would explain that the system failed because it treated a partial dependency failure as a full dependency. Requests blocked waiting for the unhealthy service, consuming resources and cascading failure. The fix is to isolate the dependency using timeouts, circuit breakers, fallbacks, or partial responses so the rest of the system can continue operating.
Why this matters in real systems.
Most large outages are caused by partial failures that were not isolated. Systems that degrade gracefully preserve core functionality and user trust even when parts of the stack are unhealthy.
Follow-up 1. Why are partial failures more dangerous than full outages?
Answer: because they are unpredictable. Some requests succeed, some hang and retries amplify load. This creates cascading failure instead of a clean stop.
Follow-up 2. How do you test for partial failures?
Answer: by injecting latency, timeouts, or error rates into dependencies rather than taking them completely offline. This reveals how the system behaves under realistic failure conditions.
Follow-up 3. Curveball. Can graceful degradation ever hurt user experience?
Answer: yes. Poorly designed degradation can confuse users or hide important failures. Degradation must be intentional, transparent, and aligned with business priorities. This scenario establishes a critical reliability principle. Systems must be designed to survive partial failure, not just total outages. Next, we'll examine how a well-timed feature flag can save a system under extreme load. Scenario 22, the feature flag save.
The interview challenge.
Traffic is climbing, latency is rising, and error budgets are burning. A non-critical feature is consuming significant resources on every request. The interviewer asks, how do you reduce load immediately without redeploying or rolling back code?
Where most candidates go wrong.
Most candidates think in terms of redeployments or rollbacks. They focus on fixing code rather than reducing pressure. This costs time during an incident and often makes the situation worse.
How senior engineers think about this.
A senior engineer looks for immediate load reduction levers. 1. Not all features are equally critical to core user journeys. 2. Some functionality can be safely disabled to preserve the system. 3. Fast control beats perfect fixes during incidents.
The interview-winning answer.
I would explain that feature flags allow rapid degradation without redeploying. By disabling non-essential features that consume CPU, I or O, or downstream calls, we immediately reduce load and stabilize the system. After stabilization, we can investigate the root cause safely.
Why this matters in real systems.
Feature flags are one of the most effective incident response tools. Teams that treat them as operational controls recover faster and with less user impact.
Follow-up 1. What makes a feature safe to disable?
Answer: it must not block core user flows and should fail gracefully when turned off. Non-critical enhancements are ideal candidates.
Follow-up 2. Why is this better than scaling?
Answer: because it reduces load instantly. Scaling takes time and may amplify downstream pressure. Feature flags cut demand at the source.
Follow-up 3. Curveball. When can feature flags make things worse?
Answer: if flag evaluation itself is expensive or relies on a failing dependency. Flags must be designed to be fast and local. This scenario reinforces a key incident principle. Removing work is often more effective than adding capacity. Next, we'll examine how systems quietly accept infinite work until they collapse. Scenario 23, the infinite queue.
The interview challenge.
Traffic increases gradually. The system continues accepting requests, error rates stay low, and dashboards look calm. Then memory usage spikes, latency explodes, and the service crashes. The interviewer asks, why did a system that never rejected requests suddenly collapse?
Where most candidates go wrong.
Most candidates assume accepting all requests is a sign of resilience. They treat rejection as failure and design systems to absorb unlimited work, not realizing that unbounded acceptance hides overload until it is catastrophic.
How senior engineers think about this.
A senior engineer treats queues as pressure regulators. 1. Queues represent waiting, not progress. 2. Unbounded queues convert fast failure into slow collapse. 3. Memory and latency grow silently while work piles up. Java code. Unbounded request queues silently absorbing overload. Disclaimer: always test code in a non-production environment. This code creates an unbounded queue. Under load, it keeps accepting requests even when workers cannot keep up. Requests wait longer and longer, consuming memory and inflating latency until the process fails.
The interview-winning answer.
I would explain that the system failed because it never applied back pressure. The unbounded queue allowed infinite waiting, hiding overload until memory and latency collapsed. The fix is to bound queues, reject excess work early, and surface overload as controlled failure.
Why this matters in real systems.
Many severe outages are caused by systems trying too hard to succeed. Controlled rejection preserves stability and protects users better than slow success.
Follow-up 1. Why is rejecting requests safer than queuing them?
Answer: because rejection provides immediate feedback to clients and prevents resource exhaustion. Queuing hides overload and delays failure.
Follow-up 2. How do you choose a safe queue size?
Answer: by calculating how much waiting time you can tolerate within your latency SLO and bounding the queue accordingly. Beyond that, rejection is safer.
Follow-up 3. Curveball. When can unbounded queues be acceptable?
Answer: for offline batch systems where latency is not user visible and storage is durable. For interactive systems, they are almost always dangerous. This scenario highlights a counterintuitive truth. Systems fail not because they reject work, but because they refuse to reject it. Next, we'll examine why failing fast often improves reliability rather than harming it. Scenario 24, the fail fast test.
The interview challenge.
A downstream dependency becomes slow but does not fully fail. Requests begin to pile up, threads block, and latency spreads across the system. The interviewer asks, why does waiting for a slow dependency cause more damage than failing immediately?
Where most candidates go wrong.
Most candidates believe waiting longer increases the chance of success. They increase timeouts and retries, assuming patience improves reliability. In reality, this approach often converts a small slowdown into a system-wide failure.
How senior engineers think about this.
A senior engineer reasons about time as a shared resource. 1. Threads waiting are threads not serving other users. 2. Slow dependencies consume capacity even without errors. 3. Fast failure protects the rest of the system from cascading waits. YAML config. Aggressive timeouts and circuit breaker to fail fast under dependency slowness. Disclaimer: always test code in a non-production environment. This configuration enforces a short timeout. When a dependency is slow, requests fail quickly instead of waiting. This frees threads and prevents queue buildup.
The interview-winning answer.
I would explain that waiting is the real enemy. By failing fast with tight timeouts and circuit breakers, the system preserves capacity for healthy requests. Fast failure contains blast radius and prevents a slow dependency from consuming all available resources.
Why this matters in real systems.
Many outages are caused by systems that wait politely for dependencies that will never recover in time. Failing fast keeps systems responsive even when parts are unhealthy.
Follow-up 1. How do you choose the right timeout value?
Answer: I base it on historical latency percentiles and the user-facing SLO. Timeouts should be shorter than the point where waiting harms user experience.
Follow-up 2. Why do retries conflict with fail-fast behavior?
Answer: retries reintroduce waiting and amplify load. Fail-fast strategies require retries to be limited or disabled during degradation.
Follow-up 3. Curveball. When is failing fast the wrong choice?
Answer: for critical, idempotent background workflows where eventual completion matters more than responsiveness. User-facing paths benefit most from fail-fast behavior. This scenario teaches a counterintuitive lesson. Reliability often improves when systems give up sooner. Next, we'll examine what happens after a system recovers, but immediately fails again under the weight of its own backlog. Scenario 25, the recovery limbo.
The interview challenge.
A system crashes under load. The team restarts it successfully. Within minutes, latency spikes again and the system becomes unstable a second time. The interviewer asks, why does a system fail immediately after recovery, even though the original issue was fixed?
Where most candidates go wrong.
Most candidates assume recovery ends once the service restarts. They focus on fixing the initial fault and overlook the accumulated backlog that built up while the system was unavailable.
How senior engineers think about this.
A senior engineer treats recovery as a controlled re-entry, not a reset one. Backlogs accumulate while systems are degraded or down. 2. Restarting releases pent-up demand all at once. 3. Sudden reintroduction of load can exceed stable capacity.
The interview-winning answer.
I would explain that the system re-failed because it was hit by a recovery surge. The backlog of queued or retried requests overwhelmed the service immediately after restart. The correct fix is to control recovery by draining queues slowly, limiting traffic, and gradually ramping the system back to normal load.
Why this matters in real systems.
Many incidents last longer than necessary because recovery is unmanaged. Systems that recover gradually are far more stable than those that attempt to resume full load instantly.
Follow-up 1. How do you control recovery traffic?
Answer: by rate limiting incoming requests, draining internal queues gradually, and coordinating retries so they don't all fire at once.
Follow-up 2. Why doesn't auto-scaling solve recovery storms?
Answer: because auto-scaling reacts after load appears. Recovery surges often arrive faster than scaling can respond.
Follow-up 3. Curveball. What's the safest recovery strategy?
Answer: start with minimal capacity, verify stability, and then increase load gradually. Recovery should be treated like a controlled rollout, not an instant restart. This scenario closes category E. It reinforces that recovery is part of system behavior, not an afterthought. Next, we move into data and caching failures, where state quietly becomes the dominant performance bottleneck.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem solving, generally most asked, and system design. Required for your software testing, job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, scenario-based questions and answers, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Category F. Data and caching.
This category focuses on a hard-earned reality. State is often the real performance bottleneck. Interviewers use these scenarios to test whether you understand how data volume, cache behavior, and lifecycle effects quietly dominate latency and throughput as systems scale.
Scenarios in this category.
1. The cache mirage. 2. The warm-up gap. 3. The data gravity drag. 4. The thundering herd. 5. The schema blocker. Scenario 26. The cache mirage.
The interview challenge.
A load test shows excellent performance. Cache hit ratio is above 95%. Latency looks great. In production, with real users, latency is suddenly much worse. The interviewer asks, how can a system with a high cache hit rate still be slow?
Where most candidates go wrong.
Most candidates assume cache hit ratio directly equals performance. They treat a high hit rate as proof that caching is working and stop investigating further.
How senior engineers think about this.
A senior engineer understands that cache metrics can be deceptive. 1. Not all cache hits are equally expensive. 2. Real user traffic has far more data diversity than test data. 3. A small percentage of misses can dominate tail latency.
The interview-winning answer.
I would explain that the cache looked effective in testing because the data set was small and repetitive. In production, higher data entropy causes more misses on expensive queries. Even with a high hit rate, the slow misses dominate P95 and P99 latency, creating the illusion that caching is working when it is not.
Why this matters in real systems.
Many teams overestimate the protection caches provide. Tail latency is often determined by the slowest uncached paths, not the average request.
Follow-up 1. Why do load tests often hide this problem?
Answer: because test data sets are small and repetitive. They produce unrealistically high cache locality that does not reflect real user behavior.
Follow-up 2. What metrics reveal a cache mirage?
Answer: cache mislatency, misfrequency by key, and P99 response times reveal whether misses dominate user experience despite high hit ratios.
Follow-up 3. Curveball. How do you test caching realistically?
Answer: by using production-like data distributions, large key spaces, and access patterns that reflect real user behavior, not synthetic repetition. This scenario introduces a critical insight. Cache efficiency is about tail behavior, not hit ratios. Next, we'll examine what happens immediately after a cache restart, when performance collapses despite correct configuration. Scenario 27, the warm-up gap.
The interview challenge.
A cache restart or deployment completes successfully. Seconds later, database load spikes, latency explodes, and users experience timeouts. The interviewer asks, why did a healthy cache restart immediately cause a production incident?
Where most candidates go wrong.
Most candidates assume a cache restart is a neutral event. They believe the cache will naturally refill and performance will recover on its own, underestimating the impact of simultaneous cache misses.
How senior engineers think about this.
A senior engineer reasons about cache lifecycle, not just steady-state one. A cold cache creates a sudden surge of cache misses. 2. All requests fall back to the database at the same time. 3. The database experiences load it was never designed to absorb.
The interview-winning answer.
I would explain that the incident was caused by a cold cache. When the cache restarted, every request became a miss, shifting all load to the database simultaneously. The fix is to control warm-up by preloading critical keys, throttling traffic during recovery, or gradually ramping cache usage instead of opening the floodgates.
Why this matters in real systems.
Cold start cache failures are common during deployments and restarts. Systems that do not manage cache warm-up trade short maintenance events for major user-facing incidents.
Follow-up 1. Why does this mostly affect P95 and P99 latency?
Answer: because some requests hit uncached paths that are far more expensive than average. These slow paths dominate tail latency during warm-up.
Follow-up 2. Why can't the database just handle the temporary load?
Answer: because databases are typically sized assuming cache protection. Sudden full load fallbacks exceed connection limits, I or O capacity, or lock contention thresholds.
Follow-up 3. Curveball. When is a cold cache acceptable?
Answer: for low-traffic systems or batch workloads where latency is not user-visible. For high QPS user-facing systems, cold caches must be managed explicitly. This scenario reinforces that cache correctness is not enough. Cache lifecycle behavior determines system stability. Next, we'll examine how growing data volume quietly breaks systems that once performed well. Scenario 28, the data gravity drop.
The interview challenge.
A query that performed perfectly in development and early production now times out regularly. Nothing changed in the code path. The interviewer asks, why does the same query slow down over time without any obvious regression?
Where most candidates go wrong.
Most candidates blame indexing or assume the database is underpowered. They focus on query syntax and tuning, while ignoring the fundamental impact of data volume growth on execution paths.
How senior engineers think about this.
A senior engineer reasons about scale effects, not just correctness. 1. Algorithms that are fast at small scale degrade as data volume grows. 2. Indexes help, but they do not eliminate I or O memory and cache pressure. 3. As datasets grow, more work moves off memory and onto disk.
The interview-winning answer.
I would explain that performance degraded due to data gravity. As the dataset grew, the query crossed thresholds where indexes no longer fit in memory and disk I or O dominated execution time. The fix is not just tuning, but designing for scale by archiving old data, partitioning tables, or changing access patterns.
Why this matters in real systems.
Many production incidents are caused by data growth, not code changes. Systems that ignore data lifecycle eventually fail under their own weight.
Follow-up 1. Why didn't load testing catch this earlier?
Answer: because test environments rarely contain production-scale data. Performance characteristics change dramatically once datasets exceed memory and cache limits.
Follow-up 2. How do you design for data growth proactively?
Answer: by planning partitioning, retention policies, and access patterns early, and by testing queries against production-sized datasets.
Follow-up 3. Curveball. When is adding hardware the right fix?
Answer: only when data growth is temporary or bounded. Long-term growth requires architectural changes, not endless vertical scaling. This scenario teaches a subtle lesson. Time itself is a performance variable as data accumulates. Next, we'll examine what happens when many users request the same uncached data at exactly the same time. Scenario 29, the thundering herd.
The interview challenge.
A popular cache key expires. Thousands of users request the same data at the same moment. Cache hit rate drops briefly, database CPU spikes, and latency explodes. The interviewer asks, how did a cache meant to protect the database become the cause of the outage?
Where most candidates go wrong.
Most candidates think cache expiration is harmless and assume misses will be spread out naturally. They overlook the fact that synchronized expiration creates perfectly aligned cache misses.
How senior engineers think about this.
A senior engineer treats cache expiry as a coordination problem. 1. Expiration aligns cache misses across users. 2. Every miss triggers identical expensive work. 3. Downstream systems experience a sudden traffic avalanche. Python code. Naive cache lookup causing a thundering herd on expiration. Disclaimer. Always test code in a non-production environment. This code checks the cache and immediately falls back to the database on a miss. When many requests arrive after expiration, all of them execute the same database query simultaneously, creating a thundering herd.
The interview-winning answer.
I would explain that the outage was caused by synchronized cache misses. To fix this, I would add request coalescing, mutex-based locking, or early refresh with jitter, so only one request rebuilds the cache while others wait or serve stale data.
Why this matters in real systems.
Cache stampedes are one of the most common causes of sudden database overload. Preventing them requires coordination, not just faster caches.
Follow-up 1. Why does this usually affect P99 latency?
Answer: because only requests arriving during the rebuild window suffer extreme delays. A small percentage of requests dominate tail latency.
Follow-up 2. What is the simplest mitigation?
Answer: adding jitter to TTL values spreads expiration over time, reducing synchronization even without locking.
Follow-up 3. Curveball. When is serving stale data acceptable?
Answer: when freshness requirements are relaxed and correctness is eventual. Serving stale data often preserves availability and performance. This scenario reinforces that caches coordinate traffic, not just store data. Next, we'll examine how a simple schema change can silently block an entire system. Scenario 30, the schema blocker.
The interview challenge.
A routine database schema change is deployed during low traffic. The deployment succeeds. Minutes later, application latency spikes, requests begin timing out, and the entire system appears frozen. The interviewer asks, how can a simple schema change block a live system without crashing it?
Where most candidates go wrong.
Most candidates assume schema changes are metadata only or fast by default. They believe that if the migration ran successfully, it could not be the cause of runtime latency.
How senior engineers think about this.
A senior engineer reasons about locks and concurrency. 1. Many DDL operations acquire exclusive table or metadata locks. 2. Reads and writes may block behind schema changes. 3. Applications appear healthy while waiting on database locks. SQL code. Schema change that acquires blocking locks under load. Disclaimer: always test code in a non-production environment. This code performs a schema change that may acquire an exclusive lock on the table. While the operation runs, concurrent queries block, causing requests to wait and latency to explode without obvious errors.
The interview-winning answer.
I would explain that the outage was caused by blocking DDL. Even though the migration succeeded, it held locks that stalled concurrent queries. The fix is to use online schema change techniques, break migrations into non-blocking steps, or run them during controlled maintenance windows.
Why this matters in real systems.
Schema changes are one of the most underestimated production risks. Systems often fail due to waiting on locks, not due to crashes or errors.
Follow-up 1. How do you detect a blocking schema change in production?
Answer: by inspecting database lock tables, long-running transactions, and queries waiting on metadata locks. Application latency with low CPU is a common signal.
Follow-up 2. Why don't retries help in this situation?
Answer: retries increase pressure on the locked table and create more waiting. They worsen contention instead of resolving it.
Follow-up 3. Curveball. When is blocking DDL acceptable?
Answer: only during planned maintenance windows with traffic fully drained. For live systems, blocking DDL should be avoided. This scenario closes Category F in the entire series. It reinforces a core lesson: systems often fail by waiting, not by crashing. You now have a complete, interview-grade mental model for performance, scalability, failure, and data behavior in modern systems.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, scenario-based questions and answers, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Reference Scenario 1, the green test that killed production.
The interview challenge.
You run a full-scale performance test. All SLAs pass. Throughput is high, latency is within limits, error rates are near zero. The system is signed off as production ready. 2 weeks after launch, under similar traffic levels, production slows to a crawl and partially collapses. The interviewer asks, how did a successful performance test miss a real-world failure?
Where most candidates go wrong.
Most candidates assume performance testing validates capacity. They focus on peak TPS, average latency, and error rates. If those numbers are green, they conclude the system is safe. This assumes that performance failures are caused by insufficient capacity.
The hidden reality performance tests rarely model.
A senior performance engineer knows most failures are caused by time, not traffic. 1. Resource leakage accumulates slowly, not instantly. 2. Queues grow over hours, not minutes. 3. Caches drift, fragment, or warm unevenly. 4. Garbage collection, compaction, and background work change behavior over time.
The actual failure mode, where nobody looks.
The performance test ran for 30 minutes. Production ran for weeks. During that time, small inefficiencies accumulated, connection pools never fully drained, cache entries fragmented memory, and background cleanup tasks competed with request handling. Latency slowly increased until queues formed. The system did not fail under load. It failed under duration.
The interview-winning answer.
I would explain that the test validated peak throughput but not steady-state stability. The failure occurred because the system was not time-stable. To catch this, I would run soak tests that last hours or days, monitor queue depth, memory growth, GC behavior, and latency drift. Performance testing must validate behavior over time, not just under load.
Why this breaks most performance programs.
Most teams test how fast a system can go, not how long it can stay healthy. Production incidents are often caused by slow degradation, not sudden spikes. Traditional load tests are blind to this entire class of failure.
Follow-up 1. What metrics reveal time-based degradation?
Answer: Q depth trends, memory usage slope, GC pause frequency, connection pool wait time, and gradual P95/P99 latency drift reveal systems that decay over time even when averages look stable.
Follow-up 2. Why don't auto-scaling or restarts fix this?
Answer: because they reset symptoms, not causes. If the architecture leaks capacity or accumulates work, scaling only delays failure. Restarts hide the problem until the next cycle.
Follow-up 3. Curveball. When is a 30-minute test still acceptable?
Answer: for stateless, short-lived workloads with no queues, no caches, and no background tasks. Most real systems do not meet those conditions. This scenario teaches a rare but critical truth. Performance is not a number. It is a behavior over time. If a candidate explains this clearly, they immediately separate themselves from 95% of performance engineers. Reference scenario 2. The load test that passed because it was too fair.
The interview challenge.
Your performance test distributes traffic evenly across all APIs and users. Every endpoint meets SLA. In production, one endpoint melts down and takes the system with it. The interviewer asks, how did a perfectly balanced test miss an obvious failure?
Where most candidates go wrong.
Most candidates assume fairness equals realism. They distribute traffic evenly because it is simple and looks statistically sound. Real systems are never fair.
The hidden reality performance tests ignore.
Senior engineers know traffic is skewed, not uniform one. A small percentage of endpoints receive most traffic. 2. Hot keys and hot paths dominate load. 3. Rare but expensive requests dictate tail latency.
The actual failure mode.
The test evenly exercised all endpoints, hiding the fact that one expensive API path dominates production traffic. That path saturated a shared resource, creating cascading latency that never appeared in the test.
The interview-winning answer.
I would explain that performance tests must model traffic skew. I would identify hot endpoints, weight them heavily in the test, and validate tail behavior. Fair tests validate code correctness. Skewed tests validate system survival. Lesson: real load is uneven. Performance tests must be unfair on purpose. Reference scenario 3. The latency test that lied because it was too fast.
The interview challenge.
A performance test shows excellent latency at peak throughput. In production, latency is much worse even at lower traffic. The interviewer asks, how can latency be worse at lower load?
Where most candidates go wrong.
Most candidates assume faster load generators mean better tests. They forget that test tools often run faster than real users.
The hidden reality.
Senior engineers understand pacing matters. 1. Load generators do not think, pause, or hesitate. 2. Real users create bursty, synchronized pressure. 3. Zero think time collapses queuing effects.
The actual failure mode.
The test smoothed traffic too perfectly. In production, real user pauses caused request bursts that filled queues and triggered tail latency. The system failed under human behavior, not raw load.
The interview-winning answer.
I would explain that latency is driven by burstiness, not averages. I would add realistic think time, synchronized user behavior, and burst modeling. Performance testing must simulate humans, not machines. Lesson: smooth load hides queuing. Humans create spikes. Reference scenario 4. The test that failed only after it succeeded.
The interview challenge.
Your test ramps up, holds peak load successfully, then ramps down. During ramp down, latency spikes and errors appear. The interviewer asks, why did the system fail when load decreased?
Where most candidates go wrong.
Most candidates stop paying attention after peak load. They assume ramp down is harmless.
The hidden reality.
Senior engineers test recovery, not just stress. 1. Queues drain unevenly after peak load. 2. Background cleanup competes with live traffic. 3. Caches and pools rebalance during ramp down.
The actual failure mode.
The system accumulated hidden backlog during peak load. When traffic dropped, internal cleanup surged, overwhelming capacity. The system failed during recovery, not overload.
The interview-winning answer.
I would explain that performance tests must validate recovery behavior. I would monitor queue drain rates, background tasks, and latency during ramp down. Recovery is a load phase, not a rest phase. Lesson: systems often fail while healing. Reference scenario 5. The passing test that ignored time alignment.
The interview challenge.
Every individual service passes performance tests. In production, when combined, latency explodes. The interviewer asks, how did isolated success create system failure?
Where most candidates go wrong.
Most candidates test services independently. They assume good local performance implies good system performance.
The hidden reality.
Senior engineers think in alignment. 1. Small latencies add up across fan-out paths. 2. Tail latency compounds across dependencies. 3. Concurrency alignment amplifies waiting.
The actual failure mode.
Each service was fast in isolation. When called together, their P95 latencies aligned, creating extreme P99 end-to-end delays. The system failed due to synchronized waiting.
The interview-winning answer.
I would explain that system latency is multiplicative, not additive. I would test end-to-end paths under realistic fan-out concurrency and validate tail behavior across service boundaries. Lesson: distributed latency compounds silently. Reference scenario 6, the test that optimized the wrong success metric.
The interview challenge.
Your performance test is optimized for maximum throughput. It achieves record TPS. In production, users complain the system feels slow. The interviewer asks, how can higher throughput make users unhappy?
Where most candidates go wrong.
Most candidates treat throughput as the primary success metric. They celebrate high TPS without considering waiting time.
The hidden reality.
Senior engineers optimize experience, not volume. 1. Throughput can increase while latency explodes. 2. Queues trade responsiveness for volume. 3. Users feel waiting, not TPS.
The actual failure mode.
The system achieved high throughput by allowing long queues. Requests eventually completed, but users waited too long. The test optimized completion, not responsiveness.
The interview-winning answer.
I would explain that performance tests must prioritize latency SLOs over throughput. I would cap queues, enforce backpressure, and accept lower TPS to preserve user experience. Lesson: fast systems finish quickly, not eventually.
The one truth performance testing never teaches.
Performance testing is not about proving a system is fast. It is about proving a system is stable over time, under skewed load, with imperfect users and partial failures. Most outages happen in places traditional tests never look: recovery, duration, tail behavior, and coordination. If you understand these scenarios, you stop testing for numbers and start testing for survival. If you can explain even one of these scenarios clearly in an interview, you immediately stand out. If you design systems with them in mind, you prevent incidents most teams never understand until production.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing, job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer. Scenario-based questions and answers. System design questions and answers where almost 90% of the people are failing to answer. With detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, You people can download all 6 PDFs in a single zip file from below given links. For more exciting tips, tricks and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.